Welcome to my talk. My name is Jonathan Prieto-Cubides. I am a PhD student at the University of Bergen, and the title of this talk is on homotopy walks and spherical maps in homotopy type theory, which is a part of a bigger project that I do in collaboration with Håkon Gilterud to express the planarity of graphs in homotopy type theory. The overview of this talk is that I will give you an overview of the concepts that I need from graph theory, expressed in type theory, to define two notions of graph embeddings on the sphere. I will give topological intuition to define them. All the results of this talk are formalized, verified in the proof assistant Agda, and you can find them available on my website / synthetic graph theory. So what is a graph? Here, a graph is a directed multigraph in the sense that we have a set of nodes and a set for edges for every pair of nodes. We also work with walks. The type of walks is an inductive data type defined in a similar way as for list. We have two constructors. We have the first constructor for the trivial walks and the second constructor which prepend an edge to a walk to give us a composite walk. In this way, we can define what it means for a graph to be connected. This is the fact that for every pair of nodes, it merely exists a walk to connect them. In the paper, I introduce the concept of quasi-simple walks to define later a refinement of the spherical maps. So a quasi-simple walk is the one that in which I permit a cycle at the end of the walk, but I I will not allow cycles at the beginning of in intermediate parts of the walk. Let's make this precise. But first, in what follows, I will assume that the node set of the graph is discrete. Alright, so being quasi-simple for a walk is a proposition that says that for every node in the graph is a proposition the fact that the node belongs to the walk. This membership relation of a node in the walk is not the traditional one. I define this by induction on the structure of the walk. We have two cases. A node doesn't belong to the trivial walk, never. And for a composite walk, E of an edge E and W, this node Z belongs to this composite walk if and only if it's the head of the edge or if belongs to the walk W. Now let's use some ideas from term rewriting systems. One can define a loop reduction relation on walks precisely to remove those cycles that we need later. Using the notion of quasi-simple for walks, I define what it means for a walk to be in normal form, which is to be quasi-simple, and also that it doesn't reduce in the sense of the loop reduction relation. One can prove that the membership relation of a node in a walk and also being quasi-simple for a walk and being in normal form are all decidable propositions. Finally, I prove a normalization theorem for walks, which says that for any walk we can find a reduction to its normal form. Now let's give some intuition about the concept of graph embeddings on a surface. So remember that the main concepts of this paper is homotopy of walks and spherical maps. I use indistinguishably the word map for combinatorial maps and for graph embeddings. So, a graph embedding or a map is a way to decompose the surface in which the graph is embedded in this way. For example, here we have a basketball ball, and on its surface you can see that there is a graph formed by these black stripes. If you remove from this surface this graph, what you obtain is a set of regions or faces. Using this set of faces, if you glue them again, you can reconstruct the surface. So this is essentially the idea behind the graph embeddings. In the paper, we use the combinatorial representation of a of a graph embedding. Let's give its type. So there exists this correspondence, this one-to-one correspondence between the combinatorial representation of a graph embedding and the topological definition. It turns out that the information that is needed to represent a graph embedding is only the cyclic order of the edges incident at each node. In traditional topological graph theory, one works with undirected graph, but here I said that we have directed multigraph. Instead, we are going to keep the cyclic order of the edges incident at each node in the symmetrization of the graph. The symmetrization of the graph is a construction similar as considering the half edges for undirected graph. As in the picture, you can see that what one is interested in is in all this information about the cyclic order of the purple edges. And the collection of these purple edges are also called star are forming the start of the graphs. So a graph may have many maps, and each map defines an implicit surface. In this case, I present the example of 6 possible maps for the bouquet B2. The maps in the first 2 columns define a surface of the 2-dimensional plane. However, in the third column, the maps define a topological torus. I also need to mention that some of these maps are equal. So there are actually just 3. I'm only interested in the maps that define the surface of the sphere. So the question is, how can I characterize those? Well, we need more topological ideas to characterize those maps. So the sphere has the property that any loop can be contracted to one point. This property is also for any simply connected closed surface, which are actually isomorphic to the sphere. In this way, we can characterize those maps that defines the surface of a sphere. I call those spherical maps. So a spherical map is the proposition that says that for every pair of walks that share endpoints, there exists, it merely exists walk-homotopy, or the way that you can deform one walk into another. Let's try to make this more precise. So homotopy for walks is an equivalence relation that considers four case to collapse phases or regions. This is the combinatorial equivalent definition of homotopy of paths, as in hot. So in the picture, you can see that one can deform the walk of orange color. You can deform along along the faces to transform it in the walk of green color W2. The details are in the paper. But this is essentially a congruence relation with a for constructor that relates two walks every time that we have a phase between them. So now I can present a refinement of the first definition for spherical maps. What I include here is that using the topological intuition that a loop can be contracted to one point, I will remove from the consideration of a walk all its inner cycles. Then, the second definition, which works for graphs with discrete node sets, says that a map is spherical if for every pair of walks that shares their endpoints, if these walks are quasi-simple, then it merely exists a deformation between them. If that happens, then the map is spherical. So as a result, what we get is an extension of the normalization theorem that I mentioned earlier. We can find the normal form for every walk, but we can also show that it merely exists a deformation to it. As a corollary of this theorem, we show that these two definitions of spherical maps are actually logically equivalent. Please check the formalization for the details. Here I present in the picture a set of different deformations, different walk-homotopies, but what we also prove is that when you consider a finite graph, it is only we can only consider the finite set of walks without inner cycles, which coincides. This is what we call the quasi-simple walks. In other words, the finite set of quasi-simple walks is enough to characterize the embeddings of the finite graphs on the sphere. This also says that we came up with an algorithm by brute force to determine whether a map is spherical or not. Let me summarize some of the content of this talk and the paper. In the formalization, and this was revealed by the formalization, we only require a subset of homotopy type theory. Specifically, we only need the intentional Martin-Löf type theory with universes, function extensionality, and propositional truncation. As mentioned earlier, assuming that the graph has a discrete node set, we can state that we can normalize any walk to a normal form that is walk homotopy to it. And we can establish an equivalence between the two definitions of embeddings of graphs on the sphere. And thank you for your attention.
Thanks. And so we have the speaker here to answer our questions. Let's see, I don't see any questions coming. Anyone? Okay, so I do have a question. So I'm wondering how exactly the homotopy type theory is helping you in your work.
Yeah. Well, as mentioned earlier, the whole point is that we want to express the planarity of graphs in hot. And in this paper, we have a subset of results that we use for that. What we need from homotopy type theory is actually the higher inductive types, like the propositional truncation to model correctly some of the mathematical properties that we want for our objects. So we, for example, in our formalization, we have different constructions that use things like univalence and also some higher inductive types. So specifically for this paper, as I mentioned, the formalization reveal, and also because of the reviewers, only these three components from MLTT were needed. So we just needed universes, the normal MLTT, propositional truncation, and functional extensionality. But we basically just work in the category of graphs, and then we use all the power of univalence to transport some of the properties and theorems.
I see.
I don't know if that answers your question.
Oh yes. You kind of also answer my next question about univalence because sometimes you
Okay.
don't really need it, but it seems that you use it.
Yeah, that actually was quite nice after the revision of this paper, because I had many proofs in which I have used univalence because it was so handy, it was so easy. But after looking at some of the proofs very carefully, I don't really need it, so I removed them. All the usage of univalence in so many parts, and then I found out that this actually applies to a wider theory, right? So, yep.
Thank you. Any other question? I don't see a question locally.
All right.
Um, let's see. Well, if there are no more questions, then let's thank the speaker again.